about to start. Yep. And then I'm going to share the screen with a brilliant picture that I found recently. So, which is actually this one, where sort of spelling. So read it very carefully. Metabolism is the second part of this module. But in order to understand metabolism, you really, indeed, yes, you really need to understand the enzymes in the first place. I showed it my wife, and my wife it took her several attempts to actually read what it says there properly. So I thought this was quite interesting. Anyway, let's head over. And I can see you. I think, yeah, we don't want to go into that, Shimek, what you do with your hands. But I understand that Moodle is open and Bernardo has kindly provided the link, and knowing him as I do, he will do it immediately again. Yes, and there is some certainty in life. That's a really good thing. Yes, King Bernardo. And that has a really good ring to it, doesn't it? Right. And we don't have any clowns today. Yeah, but let's not worry about that. Don't you dare, Hassan. And absolutely right. Clowns give to the pizza fund. Usually somebody would put a mood underneath that comment. Thank you. Okay, hey guys, let's get started because the dogs want to go for a walk, and I want to do things. So a good point. Okay, so last week I showed you that there is one equation that every okay, that every biochemist needs to know this famous equation, this famous Michaelis Menten equation. We said we have, that's not the right pen. We said we have a reaction where we have an enzyme plus a substrate, and there is a sort of a reversible binding process where we form an enzyme substrate complex, and then we are looking at an irreversible process here which gives us the product plus the enzyme, which is recycled and can start a new round of activity again. So that's our general sort of scheme, which we will really explore a lot in this first part of this module. We said we can write that with a forward rate constant, K forward, and a reverse rate constant, let's call it reverse rate constant, KR. And this here, this irreversible step, this is generally referred to as K cut. That's the rate constant for this process. And we then said that the rate of how the substrate is basically used up can be written as the rate, and we usually abbreviate that with a V for Victor in the international alphabet. The rate V equals something that is called Vmax, and we will discuss today what this Vmax, actually what this tells us. Vmax times the substrate concentration divided by Km plus the substrate concentration. And the V can be velocity, rate. In fact, actually, probably the best thing would be to see that as a speed here, because we are not really caring very much which direction this whole thing goes. So we have Vmax here, and that is the maximum speed, maximum rate, so Vmax. And we achieve this maximum rate when all the active sites of the enzyme, active sites are occupied with substrate. Occupied by the substrate. So that means every single enzyme molecule that we have, every single one has a substrate bound. So every single enzyme is in this ES state where it has a substrate bound, and the substrate is bound to the active site. This is when we reach Vmax. So when we reach Vmax, all the active sites are occupied by the substrate. Km, we said this is a sort of a constant. And this is composed of, or it comprises the rate constants, the forward rate constant, the reverse rate constant, and the K-cut rate constant. It's made up of these three constants. This here is the rate of the reaction, and of course S, that is, how do I do that? S is the substrate concentration. Substrate concentration. Okay, so that is the Michaelis Menten equation. I also told you in the last session that this Vmax is actually the product of the total enzyme concentration times the rate constant K-cut. So that is what your K-cut, what you mean. This is K-cut. That's this one here, this rate constant. So we said Vmax equals the total enzyme concentration times this K-cut. That means Vmax depends on the enzyme concentration. And if I double the enzyme concentration, Vmax will double as well. Km, does this depend on the enzyme concentration? Does Km depend on the enzyme concentration? Dennis, you're absolutely right. It does not depend on the enzyme concentration, so I write it like that. It does not depend on the enzyme concentration. I can mess around with the enzyme concentration. Vmax will change, Km will not change. Even if I increase the enzyme concentration, Km is just simply a constant. And the constant in this context does not change. Okay, so does that make sense? Yeah, are you happy with that? That's, I think, where we stopped last time. We also said something about the conditions. So where we can apply this Michaelis Menten equation, we said no product P has formed. We said that the substrate concentration must be much larger than the enzyme concentration that we have. And we also said that the process, well, let me write it as reaction is irreversible. So that means it goes only in one direction, like this here. That is a one-way street. So these are the three conditions under which we can apply the Michaelis Menten equation. And that's very important, or where we can apply the irreversible Michaelis Menten equation. These are the three conditions. If one of these assumptions is not met, then usually the this equation that I just showed you will not work properly. It will break down, and that's you know, that's not a good thing. Now, let me write this down again. Well, that's a good point. Yes, I probably should say that. Thank you for reminding me. We also need to measure, thank you, that's well spotted. We need to measure the reaction right at the beginning, at the start. So that is, we need to get the initial rates. Very good point. Thank you very much for reminding me. That's very helpful. Yet this is pretty much the same statement as this one here. So if we measure the reaction right at the beginning, then no product has formed yet, because we are just starting with the substrate and no product has formed. That is what I mean by this. And when I say we measure, right at the start, we measure the initial rates, it means that no product is there. Yep. Okay. So how would that actually look like if we take these measurements? Because we did that in the kinetics when we had, for example, the substrate concentration and the rate. And we found something like that. What order of reaction was that? You remember? Yep, excellent. That was a zero order of the reaction. And if we did, again, we did rate and we had substrate concentration and we saw something like this. This was, of course, was a first order reaction. Now let's see how this Michaelis Menten equation relates to this order. So what would happen if we have substrate concentrations and measure the corresponding rates? Which one will we get? Will we get a zero order or will we get a first order reaction? What do you think? What will we get? Zero or first? Ellie says first. Joby says zero, both. Okay, let's see how we do that. So here I've got I've done my enzyme reaction, if you like. So I've got substrate here in column A. And in column B, I have my corresponding rates. And now let's see what this reaction actually looks like. So I hope I can do that here. I'll do that in Google Sheets, but you can do that also in Excel. So I want to put in a chart. And look at this, what I get here. So you can see the dots. And let me see if I can do that as a line chart. So what we see here is actually a fairly weird curve, isn't it? Let me see if I can. Can I take a picture of that? Actually, you see, this is a strange curve, isn't it? Let me replicate that here, where we can look at it in more detail. So here we have the substrate concentration, and here we have the rate. And what we see is something like that. And this is, we plot substrate concentration versus the measured rate versus the measured initial rate. So the substrate concentration would be, for example, in millimolar, and the rate would be, for example, millimolar per minute. And what we see is this weird curve. And so it is neither really a first order reaction, nor is it a zero order reaction. Now that's really, really strange, isn't it? But this is what is generally known as a Michaelis Menten plot. Michaelis Menten plot, because it uses the equation V, that's our rate, V equals Vmax times S divided by Km plus S. That is when we plot this equation. And now you obviously say, right, how did we get this weird thing? What does this actually mean? What's the meaning of life and things? Now, let's look at this equation and try to figure out how we get from this equation to this graph here and what these different things actually mean. Okay, so the meaning of life is 42, absolutely right. So what we see is one thing that's quite important with this Km plus S. We have got a mathematical expression where we have Km plus S in it. There are, of course, there are equations for zero and first order graphs. We have done that in the BI301 module. Remember, I showed you the equations, and we even did the integration of these equations. So yes, there are, but they don't apply here because technically speaking, we don't have a zero or first order reactions when we look at the enzymes. So we said Km plus S. We have that here in the denominator. And this already tells us something. It tells us that Km must have the same unit as the substrate concentration, because otherwise we would not be able to add them. So only if two items have the same unit, we can add them mathematically. So Km always has the same unit as the substrate concentration. So Km has the unit of concentration. Okay, so that's great. That's good to know. Now let's do a little bit of scenarios. Okay, let's say we have a scenario where we have the substrate concentration is much larger than Km. Reynolds, you are absolutely and 100% spot on. This is the fraction bound equation in thermodynamics, in a lot of physical chemistry problems, actually. Well done. And this is also how this equation was derived, because one of the people who discovered it was actually by training a physical chemist who looked at how a compound adheres to a surface. So that is where this comes from. Well done. Now, if we have our substrate concentration is much larger than Km, what we can write is Km plus the substrate concentration. And if the substrate concentration is larger than Km, much larger, then this is roughly, we can substitute that, and I indicate that with this double wavy thing. We can substitute this by just simply saying this is similar or very close to S, to the substrate concentration. And if you don't believe me, you can very easily check that. Let's say we said Km, we put in 1, and for S we put in 1000. Yeah? So 1000 undoubtedly is much, much larger than 1. What do we get for the sum of Km plus S? What do we get for the sum of Km plus S? Ooh, yeah, get it out. 1001. Absolutely right. We get 1001. And this 1001 is pretty close to our 1000. So we can easily substitute, instead of Km plus S, we just simply can say S, because S is so much bigger. Okay, so with this, let's write our Michaelis Menten equation. We write Vmax times S divided by Km plus S. That was the original one. And then we say, instead of Km plus S, I write just simply S, because S is so much bigger, right? So, oh, look, what can we do with this? What I've just written down. Nice one. The S cancels out. And what we have got left is V equals Vmax. Our rate equals Vmax. Wait for it, Edith. Wait for it. We're coming to that. So, what does that actually mean for our plot? We have S, we have V, we have our Michaelis Menten curve, and when S is very large over here, then the rate will be Vmax. And if I make S a little bit larger even, the rate will still be Vmax. So what happens is that this curve plateaus off. It will be a parallel line to the x-axis. And this value here that it approaches, this is our Vmax. That's the maximum velocity. Absolutely right. S is so big, it makes Km absolutely insignificant. So the rate will be a parallel line. Remind me again, what order was that? When it's a parallel line? It was a zero order reaction. Absolutely right. So at high substrate, let me write it like that, at very, very high substrate concentration, and I write it like that, almost like a little house, it means that it's very, very high. Substrate concentration is very high. We get Vmax. And if you think about it, what I told you earlier, Vmax we get, I think I wrote it here somewhere. Yes, we get Vmax when all the active sites are occupied by the substrate. When do we get this? When we have lots and lots of substrate present, right? So when the substrate concentration is very, very high, we get Vmax. Or we can turn that around and we can say Vmax tells us how the enzyme behaves. Enzyme behaves when the substrate concentration is very high. Oops, not height, high. High. When the substrate concentration is very high. Actually, it's not exactly true. Will we actually ever reach Vmax? Is it possible to reach Vmax? Absolutely right. We will never be able to fully reach Vmax. It's never possible. Absolutely right. We cannot get Vmax. We get Vmax. So strictly speaking, Vmax only possible if the substrate concentration is infinite. We will never reach it, but we are getting closer and closer and closer. So that's one thing. So if the substrate concentration is very high, then we get Vmax. Does that make sense? And you've done that in BI301, haven't you? Did you do that in BI301? I think with Dr. Richard Williamson. Fantastic. So now let's do it the other way around, okay? Let's say we have a substrate concentration which is much, much smaller than Km. So instead of Km plus S, I can write, what can I write now? Substrate concentration is much, much smaller. Bingo, spot on. I can write Km. Excellent, good thinking. So I can write rate V equals Vmax times S divided by Km plus S. That was the original, and that is pretty close to Vmax times S over Km. Right? What do we do with that? Well, I can write it in a slightly different format. I can write it as Vmax over Km times S. It's exactly the same. And what we get is actually another quite important parameter for the enzyme. It is this thing, Vmax over Km. Vmax over Km, I don't think it has a special name. Km can be higher, can be lower, can be the same as S. We can modify S like we want. We offer different substrate concentrations. What you probably got confused about, Edith, is we are saying that the substrate must be higher than the enzyme concentration. But Km just simply is these rate constants mixed together. Yeah. So Km can be anything, and the substrates we can vary. So this Vmax over Km, the value for Vmax over Km, it tells us how the enzyme behaves when the substrate concentration is very, very low. When it's almost zero, and again, this gets then into conflict with the Michaelis Menten equation, but theoretically, we get this Vmax over Km when the substrate concentration is very, very low. As soon as one enzyme molecule loses its substrate because it starts a new cycle, here, as soon as an enzyme loses the substrate and goes back, it's no longer in this ES complex, and therefore we are not at Vmax. So we can never, ever reach the true Vmax, but we get very, very close to it. And likewise, this Vmax over Km is a very, very important parameter that tells us how the enzyme behaves when the substrate concentration is extremely low. Yeah, does that make sense? So that is another important parameter, Vmax over Km. Well, it goes pretty much on the playlist. It is what you see here, more or less. Now, what do you think? We said Vmax depends on the enzyme concentration. Vmax depends on the enzyme concentration. Does Vmax over Km depend on the enzyme concentration? Does this value, Vmax over Km, does this depend on the enzyme concentration? What do you think? We have two conflicting opinions here. Now let's disentangle it. Km does not depend. Vmax depends, and therefore Vmax over Km depends on the enzyme concentration. On the enzyme concentration. So our Vmax over Km depends. On the enzyme concentration. Right. So far, so good. So we have Vmax. This is when the substrate concentration is very, very high. We have Vmax over Km. This tells us when the substrate concentration is very, very low. Okay, Daria, here's something for you. I write another Vmax, but I don't want to see you cry. When do we have this Vmax over Km? we have substrate concentration, we have the V, we have our Michaelis Menten plot here, where we have our Vmax here. So that would give us Vmax. And Vmax over Km is basically this point here, is this gradient here, right at the beginning. That is Vmax over Km. Okay, so we've got Vmax, we got Vmax over Km. So let's do a third scenario. Let's say our substrate concentration equals Km. Okay? This is at a certain point. We said S is very small, that's this one here, or S is very large, much larger than Km. So what happens if S equals Km? Okay, rate equals Vmax times S divided by Km plus S. And instead of Km, I just simply can write, in this case, S. I can write Vmax times S divided, and instead of Km, I can write S. S plus S. And I can put these two S together. So that's the same as, and Reynolds has already written it down, S divided by 2S. The S cancels out, and I get equals 1/2 of Vmax. Or in other words, Km, when Km equals S, so if Km equals S, then the rate equals 1/2 of Vmax. You seen that? Yes, Edith, absolutely right. Did you understand what it means? Probably not so much. So now you do. Hey, great learning opportunity. Fantastic. So when we have Km, when our substrate concentration is identical to Km, we reach 1/2 of the maximum velocity. So how do we do that? We do our substrate concentration, we do our rate. Here is our Michaelis Menten plot, like that. Yeah, you can do Vmax over 2 Km, but it doesn't help you anything realistically. It has to be exactly the same to get exactly 1/2 of Vmax. So this point here, This gives us our Vmax. This gives us our Vmax. And what do we need to find in order to get this Km from the equation? Well, what we do is we just simply take, we say this is Vmax. All we need to do is we need to take half of Vmax. 1/2 of Vmax. So that is probably this point here. This is half of Vmax. And this point here on our graph, this is the rate which is 1/2 of Vmax. Yeah, does that make sense? This is half of Vmax. And the corresponding substrate concentration, that's this guy here. This is the substrate concentration here. The substrate concentration that gives 1/2 of Vmax. And that is the same as Km. So Km is the substrate concentration. Km is the substrate concentration that results in half of maximum velocity. You mean Km, not Kd. Yes, absolutely right. So Km is the substrate concentration at which we reach half of the maximum velocity. And please bear in mind, Km has the unit of the substrate concentration. It is the substrate concentration that results in half maximum velocity. Yes, it is. So I can write this also as Vmax. Km is the substrate concentration where we have half of Vmax. Now, what does this Km actually tell us? Km tells us about how much the enzyme likes the substrate. And that's a very important concept, and I've sort of made it easier to think about it. If we have a very low Km, low Km means we need only a small substrate concentration to achieve Vmax, or to achieve half of Vmax. Yeah, you can. Yes, you can actually phrase it like that. Although it's a little bit more complex because you've got also how likely the enzyme is to bind and also then to transform it into a product. Remember, Km is this combination of these three rate constants. But in principle, you're absolutely right. So low Km means that the enzyme very much likes the substrate. So low Km, enzyme, and let's phrase it a little bit more scientifically, enzyme has high affinity for the substrate. So low Km, high affinity. It likes the substrate very much. My Km for chocolate is extremely low. Km is not just the dissociation constant, because Km also includes Kcat, which is then the third constant. Smashing. High Km therefore means low affinity. Low affinity for the substrate. I have personally a very high Km for oysters. So high Km, low affinity. And that actually puts us in a really nice position to compare enzymes or substrates. I can say, for example, enzyme has a Km of Km equals 0.1 millimolar for substrate 1 and Km of 100 millimolar for substrate 2. Which substrate does the enzyme prefer? You can only compare them with each other. If you just simply have a Km of, say, 0.1 millimolar, it doesn't tell you anything in comparison. You only can compare them if you've got two. But you're absolutely right. The Km of 0.1 millimolar indicates that the enzyme really loves substrate 1. It has a very high affinity because we only need a very low amount of the substrate in order to get half of substrate 1 to get half of the maximum velocity. For substrate 2, we need far more substrate to achieve the same effect. So the enzyme has a very high affinity for substrate 1 compared to substrate 2. Does that make sense? Fantastic. So What you've learned today, and you did a lot of stuff today, we learned how a Michaelis Menten plot looks like, that it is a weird mixture of first order reaction, which happens here, and zero order, which is extreme here, and then we change everything in between here. We learned how we can find Vmax, or we can at least approximate Vmax. This is when we have very high substrate concentration, and I've written it down here. If the substrate concentration is very high, we get Vmax. So Vmax tells us how the enzyme behaves when the substrate concentration is almost infinite. We learned about the parameter Vmax over Km that tells us how the enzyme behaves when the substrate concentration is very, very low, almost zero. And we know that Vmax over Km is dependent on the enzyme concentration. And finally, we discussed what happens if the substrate concentration is equal to Km. And in this case, we get half of the maximum substrate concentration. So in a way, what we could do in order to find this Km is we can do our measurements. We get the plot here, and then we can just simply say, right, let's see what is our Vmax. So let's say that's here Vmax. And all I need to do is I need to find half of Vmax. It's about here. So that's half of Vmax. And what I need to do is I need to find the substrate concentration that produces this half of Vmax. So that would be our Km here. And that is how you, in theory at least, can find Km. Happy with that? And with that, we basically can really write our Michaelis Menten equation, because we found the two things that we are looking for. We found Vmax and Km. Fantastic. So what I'm going to do on Friday is I will do a little bit of calculations with the Michaelis Menten equation, and I think there are some YouTube videos on the playlist. So if you want to have a sneak preview, but you don't have to, because we are going through these calculations in the session on Friday. Without any further ado, the dogs are waiting. And at one point, I will show you them live and in action. And thank you for watching, and have a fantastic afternoon. And I'll see you tomorrow for BI308, or most of you. Take care. Bye-bye.